We are going to the moon, and we are going there to stay this time. That's the plan that the American government, NASA, and dozens of their international and commercial partners have committed to. Not a temporary visit. Not a brief landing followed by a hasty retreat back to Earth. This time, when human boots touch lunar soil again, those astronauts won't just plant flags and collect rocks. They'll start building something that has never existed in human history, a permanent settlement on another world. And assuming that they can stick to this plan, assuming the funding doesn't dry up, the technology doesn't fail, and the political will holds strong across administrations and decades, what we are looking at is so much more than just landing people on the moon. Landing is impressive. Landing is dangerous. Landing requires extraordinary engineering and courage, but landing is not easy, and it's also not the hardest part of this mission. We have done that before. 12 astronauts walked on the moon between 1969 and 1972, during the Apollo program's golden age. We know how to get there. We know how to land safely. We know how to survive for a few days in spacesuits, exploring the surface, conducting experiments, then returning home with samples and stories. But what comes next, what NASA and its partners are planning for the 2030s, is something entirely new. Something that has never been attempted. Something that will require us to solve problems we've never faced before, using technologies that are still being invented. We need to build on the moon. We need to build a permanent base, capable of supporting human life not for days or weeks, but for months and years. Essentially, a small city on an alien world. A settlement with roads and power plants, habitats and laboratories, greenhouses and garages. A place where people can live and work without constantly relying on supply missions from Earth. A place that can sustain itself using local resources, lunar water, lunar minerals, lunar energy. And no one is exactly sure how that's going to go. The challenges are immense. The moon is not a friendly place. It has no atmosphere to protect us from radiation or micrometeorites. It has no magnetic field to shield us from solar storms. The temperature swings are extreme, scorching hot in direct sunlight, freezing cold in the shadows. The gravity is only 1/6 of Earth's, which sounds convenient but actually creates all sorts of biological and engineering problems. And perhaps most insidiously, the entire surface is covered in a layer of razor-sharp dust that destroys machinery, clogs filters, and can even damage human lungs. Building a city there, a functioning, sustainable city, will require rethinking everything we know about architecture, infrastructure, transportation, and energy production. We can't just copy-paste Earth solutions and hope they work. The moon demands entirely new approaches. But we do have some incredibly practical and innovative new solutions for life beyond Earth. Solutions that sound like science fiction, but are already being tested in laboratories and space stations. Solutions that will transform humanity from a single planet species into something more. Explorers, settlers, builders of worlds. The moon is the first step, the proving ground. If we can make it work there, we can make it work anywhere. First, we need to talk about where this moon base is going to be located. Because the moon is a big place, roughly the same surface area as Africa, and every previous human landing has happened in the same general region. Right around the middle, in the lunar Maria, those vast plains of ancient lava flows that appear as dark patches when viewed from Earth. The Apollo missions specifically targeted the equatorial regions because they were nice, flat, and safe, perfect for landing a delicate spacecraft. The terrain was predictable, without too many craters or boulders to dodge during descent. And crucially, These locations allowed for direct radio communication with Earth. The astronauts could look up and see their home planet hanging in the black sky, always in the same spot, making communication simple and reliable. But that was the 1960s. That was a different era with different goals. Those missions were about demonstrating capability, about winning a geopolitical competition, about proving that humans could reach another world and return safely. The science was important, but secondary. The engineering triumph was the point. This time, when we return to the Moon with the Artemis program, we are aiming for a much more interesting and infinitely more challenging location: the lunar South Pole. This region couldn't be more different from the flat, sun-drenched plains where Apollo landed. The South Pole is rugged, ancient, mysterious. The terrain is littered with impact craters, some small enough to step over, others deep enough to swallow mountains. There are mountain ranges here, peaks that reach higher than any mountain on Earth relative to their surroundings. There are ancient volcanic formations, evidence of a moon that was once geologically active, with lava tubes that might provide natural shelter for future habitats. And most intriguingly, most importantly for long-term settlement, some of the low valleys and deep crater beds are in permanent shadow. The geometry of the Moon's slight axial tilt, only 1.5 degrees compared to Earth's 23.5 degrees, means that the Sun never rises high enough to illuminate the deepest craters. The floors of these craters haven't seen direct sunlight in millions or billions of years. Think about that for a moment. These are places that have been dark longer than complex life has existed on Earth, longer than the dinosaurs walked, longer than the continents took their current shapes. These shadows are as old as the Moon's current geological era, and because they've been cold and dark for so long, scientists believe they contain something invaluable: water ice. Not liquid water. The Moon's lack of atmosphere means liquid water would instantly boil away into space. But frozen water, preserved in these permanently shadowed craters like a cosmic freezer. This water was transported to the inner solar system billions of years ago on asteroids and comets. When these icy bodies crashed into the Moon, some of that water ended up in the cold traps of the South Pole, where it has remained ever since, accumulating over geological time. This water is worth more than gold, more than any precious metal, more than any other resource we could find on the Moon. Because water means everything for a lunar base. You can drink it, obviously, but you can also split it into hydrogen and oxygen, fuel for rockets and vehicles, oxygen for breathing. You can use it to grow food in greenhouses. You can use it as radiation shielding, because water is excellent at absorbing harmful cosmic rays. Having accessible water on the Moon changes the entire calculation for sustainability. Instead of shipping water from Earth at thousands of dollars per kilogram, we can mine it locally, process it locally, use it locally. That's the difference between a temporary outpost and a permanent settlement. NASA has identified 13 potential landing sites for the Artemis program, all concentrated near the South Pole. These aren't chosen randomly. Each one represents a careful compromise between scientific opportunity and survivability. They are mostly on little patches of elevated ground, crater rims, tops of low mountains, where sunlight is available for most of the lunar day. These peaks of eternal light are surrounded by deep shadows and rough terrain, with the precious water ice deposits potentially just a short drive away in the permanently shadowed craters. It's a landscape of extremes. Brilliant sunlight just meters away from pitch-black shadows, ancient ice neighboring sun-baked rock, smooth landing spots adjacent to boulder fields and steep slopes. This will be a deeply fascinating region for scientific discovery. The ice cores from these cold traps could tell us about the history of water in the early solar system. The ancient rocks could reveal secrets about the Moon's formation and the violent early period when Earth and Moon were bombarded by countless impacts. The permanently shadowed craters are time capsules, preserving material that hasn't been altered by sunlight in eons. But it will be equally, if not more, dangerous for the people who need to live and work on the Moon for weeks and months at a time. The terrain is treacherous. The shadows are disorienting. The temperature differences between sunlight and shadow can be hundreds of degrees. Navigation will be difficult. Landing will be nerve-wracking. Every excursion outside the safety of the base will carry risks that the Apollo astronauts, working in the relatively benign equatorial regions, never faced. So, this is going to require infrastructure like we've never seen before. All of the fundamentals that make a city on Earth possible, roads, buildings, power, transportation, need to be recreated from scratch in the most hostile environment imaginable, with the most limited resources available, under constraints that seem designed to make the task impossible. We need to reinvent civilization using only what we find on the Moon, what we bring in the limited cargo capacity of our spacecraft, and what we can manufacture with robotic and 3D printing technology. So where do we begin? What's the first thing we need to build? The answer might surprise you. Roads. Yes, where we're going, we absolutely need roads, and landing pads, and walkways, and solid, stable surfaces around our habitats and work sites. Because the first and most insidious enemy we face on the Moon isn't radiation or cold or lack of atmosphere, it's dust. The lunar surface is coated in a relatively thin, yet incredibly problematic layer of ultrafine regolith, powdery material created by billions of years of meteorite impacts, pulverizing the rock into smaller and smaller particles. This lunar dust is unlike anything we have on Earth. Each grain is sharp and abrasive, like broken glass, with jagged edges that haven't been smoothed by wind or water erosion because the Moon has neither. Under a microscope, lunar dust looks like tiny shards of razor blades. During the Apollo missions, this dust proved to be one of the most annoying and dangerous challenges the astronauts faced. It was known to cut through the outer layers of spacesuits, not immediately, but after repeated exposure, the suits would develop weak spots and micro-tears that could have been catastrophic if left unrepaired. The dust scratched the glass visors on helmets, gradually reducing visibility. It got into every seal and joint, degrading equipment performance. One astronaut described the smell of lunar dust that clung to their suits and was brought into the spacecraft as resembling burnt gunpowder, an acrid, metallic smell that wouldn't go away. To make matters worse, the dust is also extraordinarily clingy. Because the Moon lacks an atmosphere, there's no weathering process to coat dust particles with oxidation layers like on Earth. Lunar dust is electrically charged by solar radiation and the solar wind, causing it to stick to everything through electrostatic attraction. It clings to spacesuits, to equipment, to solar panels, to radiators, covering surfaces with a fine gray coating that's incredibly difficult to remove. During one Apollo mission, dust accumulation on the lunar roving vehicle caused it to overheat. The dust clogged up the radiator fins that were supposed to dissipate heat, acting as an insulating blanket that trapped thermal energy. In an environment where equipment cooling is already a challenge, this was a serious problem that could have ended the mission early. But here's the real trick that makes lunar dust so dangerous for a permanent base. Without atmosphere and with very little gravity, only 1/6 of Earth's, once you kick up dust, it can really travel. It doesn't settle quickly like dust on Earth. It doesn't get carried away by wind because there is no wind. Instead, it follows ballistic trajectories, shooting out from wherever it's disturbed and landing far away, coating everything in its path. When Apollo 12 landed on the Moon in November 1969, the astronauts had a specific mission objective. They were trying to get as close as possible to an unmanned probe called Surveyor 3 that had soft landed on the lunar surface 2.5 years earlier. NASA wanted astronauts to inspect it, photograph it, and retrieve some components to bring back to Earth to see how they had weathered the lunar environment. And what they found was startling. Even though the Apollo lunar module had landed 180 meters away, nearly 2 football fields distant, the Surveyor probe had been sandblasted by dust that the rocket engines had kicked up during the Apollo descent. The white paint on Surveyor's surface was darkened and discolored. Components that should have been pristine were coated in a fine layer of abrasive material. The probe had essentially been hit by a dust storm traveling at high velocity, propelled by the exhaust from engines that were more than the length of a football stadium away. Now imagine a permanent moon base where rockets are constantly landing and lifting off, where rovers are driving around every day, where astronauts are walking outside regularly, where construction equipment is digging and moving regolith for building materials. Every single one of these activities kicks up plumes of dangerous, abrasive, clingy dust that spreads across the entire base, coating solar panels, degrading seals, working its way into every mechanism and joint. If we are going to build a sustainable city on the Moon, where people are living and working continuously, where sensitive equipment needs to function reliably for years or decades, where solar panels need to generate maximum power without being covered in dust, then we need to do as much as possible to eliminate, or at least control, the dust problem. That means we need roads. Solid, stable surfaces that don't generate dust clouds when vehicles drive across them. Landing pads where rockets can set down without blasting loose regolith across the base. Hardened areas around habitats where astronauts can walk without stirring up clouds of abrasive particles. The quick and dirty answer in the short term, something we could implement with the very first Artemis missions, might be a product with an unfortunate but memorable nickname, rhino snot. That's not its official chemical name, obviously. It's a spray-on polymer solution that the U.S. military uses to stabilize dirt roads, helicopter landing pads, and other unpaved surfaces in field operations. The name comes from its appearance and consistency when being sprayed, thick, gooey, and decidedly unglamorous. Rhino snot was widely used in Afghanistan and Iraq, particularly in the desert regions where loose sand created huge problems for military operations. When helicopters would land or take off, they'd create massive dust clouds that reduced visibility to zero, making operations dangerous and alerting everyone in the area to the helicopter's presence. By spraying the landing zones with this polymer solution, the military could bind the sand together, creating a stable surface that didn't produce dust clouds. For the Moon, the concept would work similarly. Before building habitats or bringing in equipment, astronauts could spray high-traffic areas with a similar binding agent. The lunar regolith would stick together, creating a reasonably solid surface that could handle rovers driving over it and astronauts walking across it without generating dangerous dust plumes. It's not a perfect solution. Far from it. First, we'd have to transport all of this binding material from Earth, which means precious cargo capacity being used for what amounts to industrial glue. Every kilogram we bring to the Moon costs approximately $10,000 to $20,000 in launch costs, so we're talking about spending millions of dollars just on dust control. Second, we'd essentially be polluting the Moon, covering pristine ancient surfaces with synthetic polymers and microplastics. From a scientific perspective, this is problematic because it contaminates the environment we're trying to study. From an ethical perspective, some would argue we have a responsibility not to trash another celestial body the way we've trashed parts of Earth. And third, it doesn't scale. Rhino snot might work for small landing pads and walkways in the early days of the base. But if we're serious about building a city, with roads connecting multiple habitats, with landing pads for frequent cargo deliveries, with extensive surface operations, we'd need enormous quantities of this material. The cost becomes prohibitive. The pollution becomes unacceptable. So a more sustainable answer, one that can actually be scaled up to build infrastructure for a small city, would be to work with what we have on the Moon, to use local resources, to transform the dust from a problem into a building material. The solution: melt the lunar surface into solid glass. This is something that the European Space Agency is actively working on right now with an experiment called PAVER, which stands for Payload for Advanced Vehicles to Explore and Reduce Lunar Dust. Scientists at ESA have been using simulated lunar regolith, material that chemically and physically mimics moon dust, along with powerful industrial lasers to experiment with melting the surface into a solid, glass-like material. The physics are straightforward. Lunar regolith is composed primarily of silicates, minerals containing silicon and oxygen, along with various metal oxides. When heated to temperatures above 100 degrees Celsius, these materials melt. When cooled, they solidify into a glass-like substance that's hard, durable, and crucially, doesn't produce dust when you drive or walk across it. This is actually an idea that dates back surprisingly far. In 1933, engineers proposed that you could pave roads through the deserts of Earth by simply melting the sand with focused heat. Makes sense, right? Glass is just melted sand. Instead of having to transport asphalt or concrete materials across vast deserts, why not just melt what's already there? The idea was wildly impractical for Earth in the 1930s. The energy requirements were enormous. The equipment needed didn't exist or wasn't portable. The process was far slower than conventional road building. And frankly, in most desert regions, the economics didn't work out. It was cheaper to just bring in traditional paving materials than to set up the infrastructure needed to melt sand. But in a future moon base, this approach might be the best option we've got. The alternative is shipping construction materials from Earth, which is phenomenally expensive, or trying to manufacture concrete-like materials from lunar resources, which requires extracting and processing raw materials, mixing precise ratios, and still might not work as well as we need. Melting the surface in place is elegant in its simplicity. No mining required, no chemical processing, no complex manufacturing. Just heat the ground until it melts, let it cool, and you have a road. Now, we probably don't have to bring a giant industrial laser to the moon, though that's certainly an option. The ESA experiments have shown that powerful lasers work excellently. A several kilowatt laser can melt a track about 10 centimeters wide as it moves across the surface, leaving a ribbon of glassy material behind. But there's an even simpler approach that takes advantage of the one resource the moon has in abundance: sunlight. Instead of lasers, what we could do is set up a large lens to concentrate sunlight onto the surface. Specifically, engineers are proposing the use of a Fresnel lens, a flat optical device carved with concentric grooves that focuses light just as effectively as a traditional curved lens, but is much lighter and easier to manufacture. It concentrates light using the geometry of those grooves, eliminating the need for a thick, heavy piece of curved glass. The beauty of a Fresnel lens for lunar applications is that it can be made from clear plastic, which is lightweight and could even potentially be manufactured on the moon from local carbon and hydrogen sources eventually. The ESA calculations suggest that a Fresnel lens just under 2.5 meters in diameter, about the size of a small car, could concentrate enough sunlight to melt lunar regolith effectively. You'd essentially have a robotic system slowly crawling across the lunar surface, dragging this Fresnel lens behind it at a carefully calculated height and angle, focusing a spot of intense heat onto the ground. The regolith would melt into a glowing, molten pool. As the robot moves forward, the molten area cools behind it, solidifying into a glassy surface. Repeat this process systematically, and you can pave roads, create landing pads, and build stable foundations for structures. However, and this is where the lunar South Pole location becomes challenging again, given the geography where the sun is low on the horizon and shadows are long and deep. Solar focusing alone might not be sufficient everywhere. In the permanently shadowed craters, sunlight concentration is obviously impossible. And even in the illuminated areas, the low sun angle means the available light energy is spread over a larger area, reducing intensity. So we might need both approaches: Fresnel lenses working in the sunlit areas, and lasers, perhaps powered by nuclear reactors or large solar arrays positioned on the peaks of eternal light, working in the shadowed regions and during the lunar night. Either way, this would be a slow process. Not watching paint dry slow, but certainly not fast by Earth construction standards. The Europeans working on the paver experiment estimate that with current technology, we could create a 100 square meter landing pad, roughly 10 meters by 10 meters. Enough for a lunar lander, with a thickness of about 2 centimeters in approximately 115 days. That's nearly 4 months to pave an area about the size of a basketball court. For comparison, that's something like 100 times slower than paving roads with traditional asphalt on Earth, where a crew can lay hundreds of meters of road per day. But here's the key insight: we have time. The lunar base isn't being built on a tight construction schedule with penalties for delays. We're building for permanence, not speed. And once we establish a robust robotic infrastructure on the Moon, with multiple melting robots working simultaneously, perhaps operating autonomously during the lunar night while astronauts rest, the pace of construction will accelerate dramatically. The first landing pad might take 115 days. But by the time we're building the 10th pad, the process will be refined, optimized, and much faster. And unlike Earth roads that degrade from weather and need constant maintenance, lunar glass roads should last essentially forever in the airless, weatherless environment of the Moon. So, we'll have roads eventually. Slow to build, but durable and effective once completed. But it's a big job, and we are going to spend a lot of time driving on the Moon as the base expands and exploration missions range farther from home. Our primary transportation will be pressurized rover vehicles, not the open-air dune buggies that Apollo astronauts bounced around in, but enclosed shirt-sleeve environment vehicles that are essentially space-age RVs. One of the most exciting examples currently in development is being created by the Japanese space agency JAXA in partnership with Toyota, the automotive giant. They're calling it the Lunar Cruiser, a deliberate nod to Toyota's famous Land Cruiser, one of the most reliable off-road vehicles ever built on Earth. But the Lunar Cruiser is something entirely different. Imagine an RV the size of a small bus, built with the engineering precision of a spacecraft, capable of traversing the most extreme terrain in the solar system. This vehicle represents a fundamental shift in how humans will work on the Moon. During Apollo, every excursion outside the lunar module meant suiting up in bulky spacesuits, going through lengthy airlock procedures, and working under constant time pressure because those suits only had limited oxygen supplies and battery power. Astronauts were constantly aware of their suit consumables, always doing mental math about how much time they had left before they needed to return to the lander. The lunar cruiser eliminates that constraint. This is a pressurized rover, meaning the interior maintains Earth-normal atmosphere and pressure. Astronauts inside can wear comfortable clothes, breathe normally, move freely without the restrictions of a spacesuit. They can work at computer stations, prepare meals, sleep in bunks, use a proper bathroom instead of the rather primitive waste management systems in spacesuits. The vehicle is designed to support 2 astronauts on extended road trips that can last for 30 days or more. Essentially, month-long camping trips across the lunar surface, traveling hundreds or even thousands of kilometers from the main base, exploring regions that would be impossible to reach otherwise. Rovers like this will be how we move around the moon base in daily operations without having to constantly get in and out of spacesuits. Think about a typical day in the lunar city. You wake up in your habitat module, have breakfast, then need to get to the laboratory building 500 meters away. On Earth, you'd walk or drive. On the moon, without pressurized rovers, you'd have to suit up, a process that takes 30–45 minutes with proper safety checks, drive or walk in the cumbersome suit. Then go through the whole decontamination and desuiting process when you arrive, which takes another 30 minutes. That's an hour of overhead just to move between buildings. With pressurized rovers, you simply step from your pressurized habitat directly into the airlock of the pressurized rover, close the hatch, drive to your destination, and step directly from the rover into the airlock of the destination building. You only need to wear spacesuits for specialized work that requires going outside, like equipment repair, construction, or geological fieldwork. The lunar cruiser would be powered by a hydrogen fuel cell, technology that Toyota has already refined for their Mirai hydrogen car on Earth. Fuel cells are ideal for the moon because they're efficient, reliable, and their only byproduct is water, which can be recycled in the base's life support systems. The hydrogen could potentially be produced on the moon by splitting water ice using electrolysis, making the entire transportation system sustainable using local resources. The vehicle will need to handle terrain that would defeat any Earth vehicle. Boulder fields with rocks the size of cars, crater walls with slopes approaching 30 degrees, areas of deep, loose regolith that could bog down wheels, and stretches of harder rock where traction is minimal in the low gravity. Now, having a capable RV for exploration and transportation is fantastic. But where do we actually live when we're at the base? What does home look like on the moon? We need to break this down into short-term accommodation and long-term permanent structures, because building a sustainable moon city is not going to happen overnight. This is a decades-long project that will proceed in phases, each one building on the successes and lessons of the previous phase. NASA has already designed our first lunar house, the initial habitat where Artemis astronauts will live and work during the early missions. They call it the Foundation Surface Habitat, and it represents the state-of-the-art in planetary habitat design. Foundation is a 3-story structure that combines cutting-edge engineering approaches, a rigid metal framework providing structural support, an inflatable module that can be compactly stored during launch, and then expanded once on the lunar surface, and advanced life support systems recycling air, water, and waste. The habitat will support up to 4 astronauts over time periods of about 1 month, though typically it will be occupied by just 2 crew members, while the other 2 are out exploring the moon in the lunar cruiser or similar pressurized vehicles. Let's take a tour, starting from the bottom. The ground level of Foundation is a metal structure approximately 4 meters in diameter, roughly the size of a large room on Earth. This is the utility and operations level. It contains the primary airlock where astronauts exit to the lunar surface, along with storage for EVA, extravehicular activity, suits. When astronauts return from excursions, they'll brush off as much dust as possible outside, then bring their suits into this level for cleaning and maintenance. This isolation helps prevent dust contamination from spreading to the living areas above. This ground level also houses a science station equipped for geological experiments with lunar samples. Astronauts can bring rocks and regolith inside, examine them under microscopes, conduct basic chemical analyses, and prepare samples for eventual return to Earth. Having this capability on the ground floor makes sense. Soil samples are heavy, and you don't want to carry them up ladders any more than necessary. Astronauts access the upper levels by climbing a ladder. In the 1/6 gravity of the Moon, this is much easier than on Earth, where a 3-story ladder climb would be exhausting. On the Moon, it feels more like climbing a single story. The second level is where the habitat gets interesting because this is the inflatable module. During launch from Earth, this entire level is compressed into a relatively small package. Once the foundation habitat is positioned on the lunar surface, this module inflates, using internal gas pressure, to expand to 6.5 meters in diameter. That's larger than any single room in most Earth houses, providing a surprisingly spacious interior. This level serves multiple critical functions. There's the hygiene station, a more polite term for the bathroom and washing facilities. In the closed-loop environment of a lunar habitat, water is precious and must be recycled. The toilet is a highly engineered system that separates solid and liquid waste for different processing paths. Liquid waste is filtered and purified for reuse. Solid waste is dried and stored, potentially for use as fertilizer in greenhouse operations or for return to Earth for analysis. Also on this level is exercise equipment. This might seem like a luxury, but it's actually critical for health. The Moon's low gravity means that astronauts' muscles and bones aren't working as hard as they do on Earth. Without regular exercise, astronauts would experience muscle atrophy and bone density loss, problems that are even more severe in zero gravity but still significant at lunar gravity. Every crew member will need to spend time each day on resistance exercises and cardiovascular workouts to maintain their health. The second level also houses a biology laboratory where astronauts will study the effects of the lunar environment on plants and animals. This research is crucial for long-term settlement. Can we grow food on the Moon? Will plants grow differently in low gravity? How does lunar radiation affect living cells? These questions need answers if we're going to build a sustainable city, and the foundation habitat will be where we start finding those answers. Going up one more level brings us to the third floor, the primary living space for the crew. This is home. There are sleeping bunks, not luxurious, but adequate, each with privacy curtains and personal storage. In low gravity, sleeping is actually easier in some ways since you don't need a heavily padded mattress. Some astronauts might even sleep while partially floating in a secured sleeping bag. There's a medical station with diagnostic equipment, a pharmacy stocked with medications for various potential issues, and instruments for monitoring crew health. The doctor is whoever has the most medical training on the crew. On early missions, probably every crew member will have cross-training in emergency medical procedures. The kitchen area includes food storage and a galley for meal preparation. Early missions will rely heavily on packaged food brought from Earth, but as the base develops, an increasing proportion of food will be grown locally in greenhouses. The kitchen's primary function is rehydrating freeze-dried foods and heating meals, though morale research has shown that even small opportunities for food preparation, adding spices, mixing ingredients, choosing combinations, significantly improve psychological well-being during long-duration missions. There are workstations with computers connected to the base's communication systems, allowing crew members to send reports to Earth, conduct research, monitor base systems, and stay in contact with families through highly delayed email and occasional video calls. The communication delay between Earth and Moon is only about 2.5 seconds, which feels almost real-time compared to Mars missions where delays are measured in minutes. And perhaps, most intriguingly, there's a human research laboratory on this level. The crew members themselves are experimental subjects in an ongoing study of how long-term habitation on the Moon affects the human body. Bone density scans, cardiovascular monitoring, cognitive testing, sleep studies, all of this data is being collected continuously, building a database that will inform the design of future habitats and help us understand what adaptations humans might need for permanent lunar settlement. The foundation habitat is impressive engineering, but it's designed for short-term occupancy, weeks to a few months. If we can get past this initial period, if the Artemis program proves successful and the lunar base continues to grow, then we need to start thinking about permanent structures. Buildings designed to last not for years, but for decades or centuries. Something that provides a genuine level of protection and security that an inflatable habitat simply cannot match. We need to insulate ourselves from the dangerous cosmic radiation that constantly bathes the lunar surface. Without Earth's magnetic field or atmosphere to protect us, radiation exposure is one of the most serious long-term health risks. We need to mitigate the effects of wild temperature swings between the 2-week lunar day and the 2-week lunar night, when surface temperatures vary by hundreds of degrees Celsius. And we need to be protected from micrometeorite impacts, tiny pieces of space debris that constantly pepper the Moon's surface at hypervelocity speeds. Without an atmosphere to burn them up, even pebble-sized meteorites retain their full cosmic velocity and can punch through thin metal walls. To accomplish all of this, we go back to the very beginning of human architecture, to the oldest building technology our species has ever developed. We build with bricks. In the same way that scientists believe we can melt the lunar surface to create glass roadways, they also think we can bake moon dust into structural bricks. The concept is similar, but the requirements are different. For roads, we need a smooth, glassy surface. For bricks, we need structural strength, thermal properties, and the ability to stack and bond them together into walls and structures. The idea is that we could still use something like an inflatable habitat, or even a solid metal structure as the core of a building, providing the pressure vessel and interior living space. But then we encase it in a shell of brickwork, building a protective layer around the fragile interior. This brick shell serves multiple crucial functions. First, it provides radiation shielding. Every centimeter of regolith between you and space reduces radiation exposure. A wall several meters thick would bring radiation levels inside the habitat down to something approaching Earth normal, safe for indefinite habitation. Second, the brick shell provides thermal mass. The material absorbs heat during the lunar day and releases it slowly during the night, helping to moderate temperature extremes. Third, it provides physical protection against micrometeorite impacts. A brick wall can absorb impacts that would puncture a thin metal habitat. Manufacturing moon bricks can be done in several ways. The simplest is to compress regolith into molds and then heat them in a solar oven to temperatures around 100 degrees Celsius. At this temperature, the lunar soil partially melts and fuses together, a process called sintering. When cooled, you have a solid brick. Early experiments have shown that lunar regolith bricks are surprisingly strong, comparable in many ways to concrete bricks on Earth, with excellent compressive strength. They can be made in standardized sizes, stacked using regolith mortar, essentially just mud made from lunar soil that's then baked in place, and built into structures of arbitrary complexity. China is particularly advanced in this research. They've been conducting experiments on their Tiangong space station using simulated lunar regolith to test brick-making processes in microgravity. They've developed a prototype device called Moonpot that can produce bricks using a combination of compression and microwave heating, technology that could be deployed on the Moon with relatively simple robotic systems. The Chinese Space Agency has even announced plans to test lunar brick construction on their upcoming Chang'e missions, potentially building small demonstration structures on the Moon before any crewed mission arrives. The vision is compelling. Imagine looking across the lunar landscape and seeing not just temporary metal structures, but actual buildings. Brick buildings with thick walls, small windows reinforced with multi-layered glass, domed roofs that shed the constant rain of micrometeorites, structures that look almost medieval in their solidity, built using techniques that humans have used for thousands of years, adapted for an alien world. But some engineers are thinking even bigger, more ambitious. Why stop at brick buildings when we could build something truly spectacular? Enter one of the wildest concepts in lunar architecture: blown glass habitats. A company called Skyports has proposed a technique that sounds like something from a science fiction novel, but is based on solid engineering principles. The idea is to use the same melting technology we'd employ for roads, but instead of creating a flat surface, you blow the molten regolith into giant bubbles, essentially creating glass domes. Here's how it would work. A specialized robot would drill into the lunar surface and insert a hollow tube. Then it would pump in air while simultaneously heating the surrounding regolith to melting temperatures using either focused sunlight or powerful lasers. As the rock melts, the air pressure would cause it to inflate like a balloon, creating a hollow dome of molten glass. As the dome grows larger and the glass spreads thinner, the robot would carefully control the heating to maintain the right temperature and viscosity. When the desired size is reached, the heating stops, and the glass cools and solidifies. The result would be a giant glass sphere partially embedded in the lunar surface, a natural pressure vessel that's also transparent, allowing sunlight to enter. With some additional processing, you could create a greenhouse, a public space, even a residential dome where people could live with a view of the stars. These glass bubbles would need additional layers for safety and insulation. You couldn't just live inside a single layer of glass. Temperature control would be impossible, and a single crack could be catastrophic. But engineers envision multi-layered structures: an outer layer of glass for structural strength and micrometeorite protection, then an insulating layer of regolith or foam, then an inner pressure layer of glass or metal. The space between layers could be filled with regolith, water, or even vacuum for insulation. The beauty of this approach is that it uses entirely local materials. No need to ship building supplies from Earth. The Moon provides the glass. The construction robots would be reusable, building multiple domes across the lunar city as it expands. It's speculative, certainly. It hasn't been tested beyond computer simulations and small-scale experiments. But it represents the kind of innovative thinking that will define lunar architecture, using the environment's limitations as opportunities, transforming the Moon's abundant regolith from a nuisance into the primary building material for an entire civilization. So we have ideas for roads, vehicles, habitats, and construction materials. We're starting to see how the physical infrastructure of a lunar city could work. But there's one critical element we haven't addressed yet, and it's perhaps the most fundamental requirement of any settlement: power. Without reliable, abundant power, nothing else matters. You can't run life support systems, you can't heat or cool habitats, you can't power robotic construction equipment, you can't communicate with Earth, you can't process water ice or manufacture oxygen You can't charge the batteries in vehicles or spacesuits. Power is the foundation upon which everything else is built. And this is where the lunar South Pole location becomes not just challenging, but potentially mission-ending without the right solution. The obvious answer, the one that works for satellites and the International Space Station and even the Apollo missions, is solar power. The sun provides enormous amounts of energy, and solar panels have become incredibly efficient over the decades. On Earth, solar power is rapidly becoming the cheapest form of electricity generation. But the Moon presents unique challenges that make solar power deeply problematic for a permanent settlement. First, there's the lunar day-night cycle. Unlike Earth, where day and night last roughly 12 hours each, the Moon's rotation is much slower. A full lunar day-night cycle lasts about 29.5 Earth days. That means 14.75 days of continuous sunlight, followed by 14.75 days of continuous darkness. During the lunar night, solar panels generate exactly zero power. For 2 weeks. Think about what that means for a lunar base. You'd need to generate and store enough power during the 2-week day to run all your systems during the 2-week night. Battery technology has improved dramatically, but storing 2 weeks' worth of power for an entire base, enough to run life support, heating, computers, research equipment, communication systems, and everything else, would require battery banks so massive they'd be impractical to transport from Earth and difficult to manufacture on the Moon. Some early lunar rovers and small robotic missions have dealt with this by simply shutting down during the lunar night. They go into hibernation mode, using small heaters to keep critical components from freezing, waiting for sunrise. But you can't do that with a crude habitat. People need continuous life support. They need warmth during the freezing lunar night. They need power for cooking, for medical equipment, for communication in case of emergencies. And it gets worse when we consider the specific location: the lunar South Pole. Remember those permanently shadowed craters that make the South Pole so valuable because of their water ice? Those same craters are the enemy of solar power. Large portions of the operational area will be in shadow all the time. Even the illuminated peaks don't receive the strong, direct sunlight you'd get at the lunar equator. Instead, the sun stays low on the horizon, reducing the effective power generation by 50% or more compared to locations where the sun passes directly overhead. Early lunar robotic missions have already demonstrated this problem in harsh terms. NASA's Viper rover, designed to explore the South Pole searching for water ice, had to be designed with extremely efficient power management because solar panels alone couldn't provide enough power to operate continuously. Mission planners expected the rover might get trapped in shadowed areas where it would slowly freeze, its battery draining, potentially ending the mission prematurely. Some missions simply die when the lunar night arrives. They freeze, their electronics fail from the extreme cold, and they never wake up when the sun returns. For small robotic probes, this might be acceptable. You get 2 weeks of data, then the mission ends. But for a crewed base, for a permanent city, this approach is obviously unacceptable. If we're serious about building a sustainable lunar settlement, one that operates continuously, supports a growing population, powers industrial facilities for manufacturing and resource processing, and enables expansion, then we need a power source that works 24/7, regardless of where the sun is. We need power that works in the shadows, power that works during the long night, power that's reliable, abundant, and can scale up as the base grows. The answer? The only answer that meets all these requirements with current technology is nuclear power. Specifically, nuclear fission, the same technology that powers nuclear submarines, aircraft carriers, and about 10% of the world's electricity generation on Earth. But scaled down, ruggedized, and adapted for the unique environment of the Moon. NASA has been developing this technology under a program called Fission Surface Power, in partnership with the Department of Energy and various commercial contractors. The goal is to create small, reliable nuclear reactors that can be transported to the Moon and provide continuous power for decades. When we say small, we're talking about reactors roughly the size of a car, maybe 3 meters long and 1.5 meters in diameter, weighing a few tons. These aren't the massive nuclear power plants you see on Earth with their iconic cooling towers and extensive facilities. These are compact, self-contained units designed to be delivered to the Moon on cargo landers, installed with minimal site preparation, and operated with minimal maintenance. Companies like Rolls-Royce, famous for their aircraft engines but also a major player in nuclear technology, have been developing these microreactors specifically for space applications. Their design philosophy is install and forget. The reactor should be able to run for 10 to 20 years without requiring refueling or major maintenance, generating power continuously the entire time. The basic principles are the same as any nuclear reactor. A small amount of enriched uranium undergoes fission, atoms splitting apart, releasing enormous amounts of energy as heat. This heat is transferred to a working fluid. Various options are being considered, including liquid metals and heat pipes. The heat drives a power conversion system, possibly thermoelectric generators that directly convert heat to electricity, or possibly a small turbine system. The beauty of nuclear power for the Moon is that it solves multiple problems simultaneously. First and most obviously, it provides power continuously regardless of sunlight. Day or night, summer or winter, though the Moon doesn't really have seasons, shadowed crater or sunny peak, the reactor keeps generating power at a steady rate. No batteries needed. No complicated power management to ration electricity during the night. No anxiety about whether the solar panels are producing enough power to get through until sunrise. Second, nuclear reactors can be scaled. The first reactor might generate 40 to 50 kilowatts, enough for a small base with 4 to 6 people. As the base grows, you add more reactors. Eventually, you might have a dozen or more scattered around the base, each one feeding into a central power grid, providing megawatts of reliable power, enough to run manufacturing facilities, resource processing plants, large-scale life support systems, and all the infrastructure of a proper city. Third, and this is especially clever, the lunar South Pole's cold environment actually helps with reactor operation. Nuclear reactors generate a lot of heat, more heat than they convert to electricity. On Earth, this waste heat is removed using cooling towers, rivers, or ocean water. On the Moon, cooling is actually a significant engineering challenge because there's no air for convection and no water for cooling. But those permanently shadowed craters, the ones that are so cold they've preserved ice for billions of years, suddenly become an asset. Place the reactors in or near these cold traps, and the extreme ambient temperature, around 40 Kelvin or 233 Celsius, provides a natural heat sink. The reactor's waste heat can be radiated away much more effectively than it could in sunlit areas where surface temperatures reach over 100 Celsius during lunar day. It's a beautiful example of turning a limitation into an advantage. The shadows that make solar power impractical become the perfect location for nuclear power plants. Now, the word nuclear makes some people nervous. And that's understandable, given the history of nuclear accidents on Earth. But these lunar reactors are fundamentally different from large power plants like Chernobyl or Fukushima. They're small, so the total amount of radioactive material is limited. They're designed with passive safety systems, meaning they automatically shut down if anything goes wrong, without requiring human intervention or electrical power. They're located far from habitats, probably at least a kilometer away, with regolith berms built up to provide additional shielding. And crucially, they're in an environment where there's no water to contaminate, no ecosystem to damage, no population at risk if something does go wrong. From a sustainability perspective, nuclear power is ideal for the Moon. Each reactor can operate for a decade or more without refueling. The fuel itself is incredibly energy-dense. A few kilograms of enriched uranium contains as much energy as thousands of tons of chemical fuel. And unlike solar panels, which degrade over time from radiation exposure and dust accumulation, nuclear reactors maintain consistent power output throughout their operational lifetime. Eventually, when reactors reach end of life, they can be safely shut down and buried in regolith, entombed in a permanent grave where their slowly decaying radioactivity poses no threat to anyone. Or, with more advanced infrastructure, the spent fuel could be reprocessed and recycled, technology that already exists on Earth but would need to be adapted for lunar conditions. With nuclear power providing the baseload, the constant, reliable power that keeps everything running, solar power doesn't become obsolete. It still has a role to play. Large solar arrays can be positioned on the peaks of eternal light, those mountaintops that receive nearly continuous sunlight. These arrays would provide supplemental power during the lunar day, allowing the base to run power-intensive operations like regolith processing, water extraction, and manufacturing without overtaxing the nuclear reactors. During the lunar night, when solar generation drops to zero, the nuclear reactors alone carry the entire load. This hybrid approach, nuclear for baseload, solar for supplemental power, provides both reliability and efficiency. It also provides redundancy. If a nuclear reactor needs to be shut down for maintenance, or if there's a problem, the solar arrays can pick up some of the slack during daylight hours. If a solar array is damaged by a micrometeorite impact or covered in dust, the nuclear reactors can compensate. The power grid itself would be a marvel of engineering. Cables buried beneath the regolith to protect them from temperature extremes and meteorite impacts, connecting habitats, laboratories, landing pads, resource processing facilities, and manufacturing plants. Smart power management systems distributing electricity based on need and priority, automatically rerouting around damaged sections, storing excess power in battery banks for peak demand periods. And as the base grows into a true city, power generation would grow with it. More reactors, more solar arrays, eventually perhaps even more exotic power sources. Solar power satellites in lunar orbit, beaming power down via microwave transmission. Or in the far future, fusion reactors using helium-3 mined from lunar regolith, the ultimate sustainable power source, fuel harvested from the very ground beneath the city. Power is the key that unlocks everything else. With reliable, abundant power, we can process water ice into drinking water, breathing oxygen, and rocket fuel. We can manufacture building materials, spare parts, and tools from lunar resources. We can grow food in greenhouses illuminated by artificial light during the lunar night. We can maintain comfortable temperatures in habitats regardless of external conditions. We can run the computers, communication systems, and life support equipment that keep people alive and connected to Earth. With power, we can not just survive on the Moon. We can thrive. We can build. We can expand. We can create something permanent. The foundation habitat becomes just the first of many structures. The initial landing pad becomes the first node in a network of glass roads connecting an expanding city. The single nuclear reactor becomes a power grid feeding growing industry. The 4 pioneers become dozens, then hundreds, then eventually thousands of permanent lunar residents. And perhaps most importantly, mastering these technologies, learning to build with local materials, to generate power without fossil fuels, to create closed-loop life support systems, to live sustainably in a hostile environment, prepares us for the next giant leap. Because the moon is not the destination. It's the proving ground. It's the gateway. Every technology we develop for the lunar city has applications elsewhere in the solar system. The habitats we design for the moon can be adapted for Mars, for the moons of Jupiter and Saturn, for asteroid mining bases. The power systems, the life support, the construction techniques, all of this becomes the foundation for human expansion beyond Earth-Moon space. If we can build a city on the moon, just 3 days from Earth, close enough for emergency evacuation if needed, close enough to resupply if something goes wrong, then we've proven we can build cities anywhere. Mars becomes achievable. Not just landing on Mars, but staying on Mars, building permanent settlements there just as we've done on the moon. The asteroid belt becomes accessible, with its resources of water, ice, metals, and rare elements. Everything we'd need to build massive space stations, interplanetary ships, and eventually the infrastructure for civilization throughout the inner solar system. Even the moons of the outer planets, Europa with its subsurface ocean, Titan with its thick atmosphere and hydrocarbon lakes, Enceladus with its water geysers, become potential sites for human presence, studied not by brief robotic missions, but by permanent research stations staffed by scientists who live there for years. The moon is where we learn to become a spacefaring civilization, where we transform from earthbound humans who occasionally visit space into a species that lives in space, builds in space, expands through space. That's the real plan behind NASA's lunar city. Not just a base, not just a symbolic presence, but the first permanent human settlement on another world, the first city beyond Earth, the first step toward a future where humanity's presence extends throughout the solar system. We are going to the moon, and this time we're building something that will outlast us all, a city that future generations will expand, improve, and eventually use as a stepping stone to the stars. The construction begins soon. The first Artemis missions will land. The first pieces of the foundation habitat will be deployed. The first roads will be melted into being. The first nuclear reactor will power up, its steady hum providing energy through the long lunar night. And humanity's second age of lunar exploration, the age not of exploration, but of settlement, will have begun.